Well, welcome everybody to our monthly engineering webinar. This is our July webinar. We hold these seminars every month, and we hope that you put it on your calendar because we have some very exciting guests that join us each month and talk about various things that's appropriate to the engineering field, both radio and television. We want to make just a real quick couple of announcements here. The ABA annual convention is coming up in August, August 12th and 13th. Those of you who are in the area and would like to attend on Friday, August the 12th, the Engineering Academy actually hosts an engineering day. And we have I think 5 or 6 presentations by noted engineers around the country. And it's a full day of engineering presentations. It's only $30 registration, which includes excellent lunch at noon. So if you can make your plans to be, you can visit the ABA website at al-ba.com and see all the information and information about the presenters. Now, our seminar each week is actually underwritten by Max Connect Group. Uh, Josh Bond and his people there with the group, they handle a lot of engineering services. They also actually have the Max Connect unit that is a special designed IP unit that can be used for remotes and backup STL. So we appreciate his support, not only for the support for this webinar, but also the support for our other activities, including the Engineering Academy classes that we have. Incidentally, our radio class is coming up in September, the week of September 12th. So if you're interested in that, you can contact us with that as well. Well, today we have a very special guest, and I want to bring in our co-host, which I think is at some mountain lodge in Tennessee. Is that where you are, or what is the deal there, John?
I wish it was that good. I'm actually stopped at the Tennessee Welcome Center on the North Carolina Tennessee line as I head on a business trip up north. So the timing was absolutely perfect to at least come in and introduce John Kean this morning. And so, Larry, while it's really nice and it's 76 degrees here, it's not a lodge.
So don't be driving and texting. just,
No,
just
definitely, definitely.
okay. All right, John. I'm going to let you introduce our special guest, and we'll continue with the program.
All right. Well, this individual is kind of one of those folks that really doesn't need an introduction. I think most of you have read articles or participated in presentations that John Kean has done. He has worked for NPR for years. That's where I first met him. He's been associated with NAB Labs. He has done numerous presentations at NAB conventions, IEEE, Broadcast Technical Symposiums, AES, and done an immense amount of work, more than I think anyone could really ever realize in dealing with HD radio, signal coverages, signal issues. And now John has decided to step into AM broadcast. And I don't know, John, if that's part of your association with the folks at Cavell Mertz these days. I know Gary's big into AM, and a lot of us are. But I know it's going to be quite an interesting presentation today that I'm sure all of you will enjoy. And so I'll turn it over to John and his AM presentation on AM Skywave. John?
Oh, well, thank you, John. Yeah, it's a pleasure being here and seeing the group, and I'm so impressed to hear about the ABA Engineering Academy from Larry. So I hope to participate as a student in that. There's always something to learn. Yeah, you mentioned Gary Cavell, and my hat's off to him. He's really the AM expert. I'm looking at this, putting my RF hat on today because I do audio engineering as well. But I was inquisitive about AM Skywave because of work I've been doing through the NRSC. And maybe if it's okay, I'll go ahead and do a screen share here and get started. You'll bear with me for a second. Let me just double check that yeah, I wanted to make sure I had share sound turned on. There we go. All right. Larry, is that operating full screen?
Yeah, that's fine. Full screen.
Good. All right. Takes a couple of seconds to get things up and running here. So, as I was saying, I've been a member of the NRSC's AM Improvement Working Group for a number of years. And one of the things that they are trying to help AM with is AM nighttime reception, in particular dealing with skywave interference. And as you know, that is co-channel interference between stations. And we hear that in part as a low frequency beat and also a modulation of the audio between the desired station and the interfering station. And that, of course, can be pretty annoying when the ratios are low between the desired and the interfering stations. Well, the AIWG has been working on a hardware solution which involves a GPS disciplined oscillator for precise carrier frequency control. This would be required on both the desired station and any co-channel interferers. And I, in my usual way, raised the question, well, who benefits from this? Do all stations? And that, of course, bounced back the question, well, you should try and find out. The project was initiated a number of years ago by members like Steve Smith and Tom King. And Steve did a study, which we see presented in this chart, back in 2007. And what he wanted to do there is find out, well, what is the audible improvement by applying precise carrier frequency control between two or more stations. And I'll just point out here, on the vertical scale, you see a sort of ITU 5-point impairment scale from objectionable, which is the worst at the top, to imperceptible interference down at the bottom. Of course, that's the best. Along the x-axis, you see the dB ratios from 0 down to -32 between the desired and the interfering carrier. Now, when you look at these chart lines, and I'm not sure if you'll be able to see my mouse pointer. It looks like it kind of disappears on the white, but the hashed line you see to the left is the results for non-synchronous operation, and the edge to the left of that is marked M. That's for music. To the right edge is V for voice. So voice service on the desired station is, of course, the most sensitive to beat interference, and it is evidenced by its position on the line here. It takes a lower ratio. And what we see in the bar to the farther right is that other hashed bar is what happens when we synchronize the carriers precisely between the undesired or interfering station and the desired. If you look horizontally across any level, let's say the long-term listenable level, there's about a 9 dB horizontal difference between the non-synchronous operation and the synchronous operation. That's what Steve Smith sees this as. And So he claims that there's about a 9 dB improvement factor by this listening test by synchronizing the two or more carriers. So the way Steve describes it, it translates into increased service areas at night. You can operate farther from the desired station and still enjoy the same level of quality that you would lose that 9 dB by operating non-synchronously. So Steve has been a proponent of this for a number of years and has been working on a hardware solution for a low-cost GPS disciplined oscillator. Well, I raised the question, as I often do in these kinds of studies. So who really benefits? Does everybody benefit? Well, ideally that would be the case, but of course there are thousands of AM stations that operate at night, and even some that operate during critical hours. And as you see here in the table, on the top row, we have Class A stations, the most highly protected, and there are 41 daytime stations, 33 of which operate in unlimited or nighttime operation. As we go down in the class scale, we see a huge number of Class B stations, 1,598, and then Class C and Class D, which have much tighter packing, as we'll see in some upcoming maps. But of the total, we have 4,000 stations, about 3,300 of which operate at night. The question is, do all of those classes enjoy a benefit in precise carrier frequency control? And if you wanted to know for any one station, your station, for example, am I one that benefits, and what is my benefit, and how many do I need to synchronize with? Well, here's a map that illustrates one class, Class A, and of course we see the United States with KFAB there in Iowa, on the Iowa-Nebraska border, enjoying a huge nighttime coverage. WBT in Charlotte, South Carolina, is over to the east, and of course they protect each other from overlap. So things work out very well for them, and maybe they don't even have very much interference at night between their two stations, unless you're maybe in that hinterland between them. Over on the West Coast, however, KFAB's signal must extend to the coast, and probably does affect those stations on the coast, that the three that are shown there. So this is a pretty manageable case. Certainly carrier frequency synchronization would be easy enough to implement with these stations, and certainly on the West Coast they would enjoy some improvement. This map is a little less obvious. This is 1160 kilohertz, and we see the nighttime ITU contour again at 150 microvolts per meter for KSL in Salt Lake City, enjoying again a huge nighttime coverage. It would certainly benefit from synchronization with those stations in places like Iowa and Dallas, San Antonio. Over on the East Coast, though, we have a pretty large grouping of Class B stations mostly, and they have a lot of overlap. the question there is the signal overlap between those stations managed enough so that all of them could synchronize and they would enjoy a benefit. So that gave rise to the modeling, which I'm going to talk about a little later. All right, now here's a case on 1230 kilohertz involving class C stations mostly, and it's pretty terrible on this channel. Overlap at nighttime is extensive. And I think we could say, even without running any computer studies, that if I'm one of those stations, I'm being covered at night by numerous other co-channel stations on 1230 kilohertz. It would be a pretty big effort to synchronize all those. They'd all need to spend the modest amount of cost. And still there would be the question, even if I'm synchronized, am I going to hear co-channel chatter in the background? And synchronization really isn't going to be a benefit. Well, that's what we're endeavoring to study. So I mentioned that there's cost-effective hardware. Steve has been working on this with others, and our working group believes that the cost would be well under $1,000 for the hardware. This would be a GPS antenna on the roof of the transmitter building, and a GPS disciplined oscillator, a buffer amplifier, a reliable power supply, and a rack-mounted panel that would feed over to the carrier frequency reference for the AM transmitter. So probably for under a couple of $1,000, this could be built and provided with instructions and an installation kit to do the job. That's at least for those stations that we're going to see about the benefit. So what I started doing was taking a look at the co-channel desired to undesired, or DDU ratios, for a large number of stations. Here's one in Homer City, Pennsylvania, WCCS on 1160 kilohertz. It is a class B directional. And what we see in this chart is the co-channel interference ratios of WCCS to all of its primary interferers. That's a pretty large list, more than 24, including quite a few international stations. I'm going to move my, there we go, so I can see some of the chart there. The worst case is WYLL, and it has a ratio of about 26 dB, followed by WCVX with a slightly lower ratio, and so on down the chart. That is a pretty favorable case for WCCS, and it's likely that by simply synchronizing with WYLL and WCVX, they would enjoy a good improvement in skywave interference at night. The question that I had was, what about all those other stations? Do they add some kind of cacophony under WYLL and WCVX that might wash out that benefit? Well, the way to find out is with that bright yellow bar up there, the RSS of all the stations combined. And we see there that that is only about -16 dB. So that is a kind of a flag to tell us that, yes, you would improve co-channel interference, WCCS, but you may find that the background noise from the other stations limits the amount of benefit. So that was one of the important things to find from this study. The question would be also how to get an up or down answer on this in a automated way. So I think we've already covered the issues in these bullets. Like is the worst case interferer critical to my nighttime coverage? Well, that can be determined by this previous chart, and we can see what the ratios are. We can also see that RSS, which tends to dilute or cover some of the benefit of the Skywave synchronization. This kind of chart also tells us how many stations we probably need to synchronize with, those in the negative 20 dB ratio range. It also identifies foreign stations, and those are a concern because they're probably unlikely to join in on a plan to purchase and install a carrier frequency kit. And if you do have any strong foreign stations that show up in this kind of listing, that is something important for stations to know. So the way I approached this was this kind of multi-step process. First was to run a Skywave nighttime search of stations for a candidate station, compute the field strengths using the F10 Skywave propagation model at the candidate site, and then rank them as we saw in that previous chart. Here's a smaller thumbnail down below here for a different AM station, KAMA. So we analyze that listing, and it's pretty easy to do visually as compared to the tabular result you see in the background. Even though the FCC takes adjacent channel stations into account for Skywave interference, we don't in this case. One of the reasons is that AM car radios these days have such high selectivity from first adjacent that they really don't enter into the Skywave interference consideration in an audible sense. It's done really more for allocation purposes. And then last would be, what kind of ratios on this chart do we really need to consider in order to know whether we have an audible problem or not? We can look at numbers, but that doesn't really tell us how listeners would perceive this interference. Well, that requires listener testing and making a simple perceptual model. That's the final step in this process. And I'm pleased to say I had the opportunity to start working with Dave Hirschberger, who's retired from Continental Electronics as their chief technical officer, a really brilliant guy and a great programmer with Octave, which is a platform that makes this kind of programming easier with a lot of tools. Also provides great audio capabilities, which we use, and we're going to talk about here in a second. So you can see in this model, what he's done is create what is a Skywave interference case we have the desired station at the top, and he simulates a carrier in software. He then simulates one or more co-channel interfering stations. Again, in software, he combines them with a fading model, which we're going to talk about, in order to provide a realistic demonstration of what the combination of these carriers sound like. And it just occurs to me that I should mention the reason we're doing this as a simulation instead of going out and recording field studies is that capturing the right conditions in field studies at night is really difficult. You have to select your combinations of stations, find the right distribution of DDU ratios from worst interferer to second worst and so on down the list. You have to deal with nighttime skywave propagation, which varies from minute to minute, varies with the day of the week and the season. And so trying to get the right conditions in order to hear a particular DDU ratio combination would be really difficult. By simulating it, we have control over all these parameters, and that's the reason that Dave developed the model. Moving along past the summation there, he creates in software simulation a real car receiver with a particular audio bandwidth, with a particular detector. In this case, it's an envelope detector, which is common to most AM receivers, and a high-pass filter. One of the things that's nice about this simulation is we can control the number of interferers as well as the ratio. So we can look at just a first interferer, a combination of first and second, and so on. And the other nice thing is there's an audio output. And so after the simulated receiver, you actually produce audio, which we can present to listeners. In the process of understanding skywave fading, I got curious about what the statistical properties are. And I found that there was really, almost no information about the temporal characteristics in a short term. There is, yes, a lot of information about skywave propagation on a long-term basis, like what's the skywave field strength, the median field strength over a period of many hours. But in order to simulate it for a listening test, we wanted to know, well, what is the rate of change and the frequency of skywave fading over shorter periods. The way I wound up solving this was to go back through and researching studies from many years ago. And this one was pretty cool. You'll notice at the top, the title of the paper I found, which was a study done by Ken Norton with the National Bureau of Standards in 1934. I had to go back that far to find this information. He measured a couple of AM stations, one of which is WLW in Cincinnati on 700 kilohertz, what we sometimes call the nation station, because they operated at such high power at one time in the early 1930s, they could be heard over most of the United States, even a good deal of the United States during the daytime. That was a power of 500,000 watts And this strip chart recording you see in the lower half is one actually made by Ken Norton and his colleagues on April 28th, 1934. It runs for 24 hours. And we see it starting over on the left during the daytime. I think this runs from 2 microvolts to 25,000 microvolts is the vertical scale. So you see during the daytime, very little co-channel interference. I'm sorry, not co-channel interference, very little signal from WLW. This was measured at a distance of 644 kilometers from WLW. So in the daytime at 50,000 watts, you weren't getting very much signal, below 10 microvolts per meter, it looks like, for most of the day. As the evening wore on, moving toward the right, we see WLW signal beginning to rise. So what I did in that blue section you see on the chart is I digitized Ken Norton's strip chart, measuring all of the changes as closely as possible. You can see a bigger enlargement of it up in this white section of the chart here. For this one was for WSM, but the principle is the same. You can see all of the points I digitized. The reason I wanted to do this was to analyze statistically what that variation was from minute to minute, and then produce it as a distribution chart. And I'm going to move my camera view over out of my way again. So in the upper right, we see this Skywave distribution chart for WLW. And again, it's in microvolts per meter on the vertical axis as a distribution of field strength bins. And what we see is a gradual increase in the occurrence of field strength, moving from left to right, and then it drops off again very rapidly. That's shown by what's happening in the strip chart, because we see that field strength values rise to a kind of median, then some pass that by a small amount, but not by as much as they drop. It's a very asymmetrical distribution with gradual rises above the median and very steep falls below the median. What this suggests is either a Rayleigh or a Ricean fading. I tend to think it's more of a Ricean fading phenomenon, because that involves usually a dominant direct path, including smaller secondary paths. Rayleigh fading usually tends to be a kind of a random mix of paths, no particular single dominant path. In any case, this tells us quite a bit about the distribution of skywave fading on a short-term basis, the way we hear it. I also wanted to point out that WLW during that 24-hour period, and this was after midnight, switched from 50 kilowatts to 500 kilowatts until it looks like about 2:30 in the morning. That's in this yellow box. So what you see there is the rise in field strength at a distance of 644 kilometers from the station, and it looks like field strengths around 10,000 microvolts per meter, which is just phenomenal. And they, I didn't digitize this because it was a shorter time period, but I thought it was really fascinating to see what was going on with WLW. And let's see, I'm going to move my camera chart back over here. All right, so here's some of the simulated audio that we prepared. Really, Dave Hirschberger gets the credit for doing this programming work. What we want to do with the audio is present it to a panel of listeners like you, who would hear unmarked anonymous samples and give ratings to them. We would then compile that listener data on the quality of the conditions that we present, and that would allow us to determine what DDU ratios are needed to provide satisfactory reception, what ratios become threshold annoying, what happens if we have more than one interferer, those kinds of things. That way we'd be able to actually put real meaning to DDU ratios. So if we look in the lower right here, Dave's produced a spectrogram where the desired station is right in the center at 0 hertz. And we see there's another carrier offset by about almost 3 hertz below it. That would be a pretty common type of frequency offset for standard crystal controlled ovenized oscillators. They could be considerably more than that. Maybe 10 hertz would be possible and barely legal, but most of them tend to group closer within a few hertz. So we see what the spectrogram looks like. In the upper center chart here, I've plotted the signal strength of the desired signal and one interferer, that one that's about 3 hertz low, over a period of time. And I'm going to actually play an audio sample so you can hear what it sounds like. Down on the chart below, you can actually see what happens to the receiver's automatic gain control. It is definitely being swung or modulated by the combination of the two carriers, and that produces a rather noticeable modulation effect. So we'll give it a try here, and maybe I'll run it for about 30 seconds so you can hear what it sounds like.
Over the last few years, but there's just not enough work. So we're seeing layoffs now, unfortunately, across the board.
So just to recap here, maybe 6 to 9 months before prices start responding, and after that, who knows?
Okay, so that was at a 10 dB DDU ratio, and I think you'd agree that was a pretty unmistakable effect due to the 3 hertz difference in frequency. I think you could hear it. All right. Now here's what it sounds like when we synchronize that undesired carrier without changing the ratios.
Over the last few years, but there's just not enough work. So we're seeing layoffs now, unfortunately, across the board.
So just to recap here, maybe 6 to 9 months before prices start responding, and after that, who knows?
Okay, that was a pretty pleasant improvement. The only problem is we also heard the audio from the co-channel interferer. So in a listening test, it would be your general opinion of the whole package, both whether there's a beat effect and whether there's background annoying audio from the undesired station. but that's how we would go about getting the ratios that are necessary to tackle skywave interference.
Over the last few years, but there's just not enough work. Over the last few.
Let's see if I can.
Yeah, we'll see. I mean, yeah, we'll see. I mean, yeah, I don't think prices are going to. Yeah, we'll.
That happened to me before. Let's see if I can get out of that. There we go. All right. This slide moves to 3 interferers, and you can see in the lower right, Dave's spectrogram showing the desired carrier in the center, one which is about 1 hertz low, one that is about 3 hertz low, and another one about 3 hertz high. And when we look at that center kind of a oscillograph in the upper center, we can see beats going on at a much faster rate this time and swinging pretty widely in gain. This is again a 10 dB DDU ratio between the desired and those 3 undesired. So here we go.
Yeah, we'll see. I mean, I don't think prices are going to come down considerably. I think they'll level, but I just don't see the market falling to any significant extent.
Vivian Geller, she's the Chief Financial Officer at a mortgage lender here in LA called Pacific Trust Group. We talk to her every now and then. Vivian, thanks a lot. I appreciate your time and your expertise, as always.
You know, when I listen to that, I have to tell myself that is a remarkably realistic reception, even though this was all done on Dave's personal computer in the Octave programming. All right, now this is what it sounds like once we synchronize those 3 co-channel stations with our test station.
Yeah, we'll see. I mean, I don't think prices are going to come down considerably. I think they'll level, but I just don't see the market falling to any significant extent.
Vivian Geller, she's the Chief Financial Officer at a mortgage lender here in LA called Pacific Trust Group. We talk to her every now and then. Vivian, thanks a lot. I appreciate your time and your expertise, as always.
So I'll look forward to your comments after the talk. To me, that's pleasantly improved, although I still hear the underlying audio from the other 3 co-channel stations, but it's it at least does not have that beat effect, and we see that here with the automatic gain control having to rapidly change gain, modulating our desired audio.
Over the last few years.
Let's see if we can.
Over the last few years, but there's just not enough.
Okay. And let's see, here's our last simulation. I did a study for KMMJ, that station that I was mapping earlier, on 750 kilohertz. It's a Class B station in Grand Isle, Nebraska. And there are half a dozen other nighttime co-channel stations on 750 kilohertz. It's a pretty quiet channel at night, which is nice. The strongest one, though, is WSB in Atlanta, which is a Class A. So it deserves the highest protection. What we're doing here is simulating what it sounds like to hear KMMJ near Grand Isle, Nebraska, hearing not only WSB coming all the way from Atlanta, Georgia on the same channel, but 22 other interferers plus WSB. And as you can see in Dave's spectrogram on the lower right here, WSB is the strongest one, and then you see a number of other Class B co-channels at lower ratios. So the nighttime interference-free contour for KMMJ is about 2.5 millivolts per meter for those who work with skywave propagation studies. So let's hear what it sounds like. See if I can back this up. There we go. And here's what it sounds like non-synchronized on KMMJ with all of its neighbors.
Over the last few years, but there's just not enough work. So we're seeing layoffs now, unfortunately, across the board.
So just to recap here, maybe 6 to 9 months before prices start responding, and after that, who knows?
Okay, well, if you can keep in mind what that sounded like, here's what it sounds like when Dave synchronized KMMJ with its 23 interferers.
Over the last few years, but there's just not enough work. So we're seeing layoffs now, unfortunately, across the board.
So just to recap here, maybe 6 to 9 months before prices start responding, and after that, who knows?
So what was noticeable to me was not the background interference of the co-channel stations programs, but that sort of gritty distortion that occurs. That involves a problem with the automatic gain control misidentifying the vector sum of the carriers and driving the detector into clipping. And that's an audible effect that is definitely improved in this case. Excuse me. So the objective here I have is to set up a listener study. And the way I'd like to do this is to use some software that I obtained from a colleague in England, which allows us to do this listener test over the internet. You can do it right on your own computer if you have speakers, preferably, although headphones would work as well. And you don't have to come into a listening room, and you don't get a stipend, sorry to say, but it allows us to do testing with a large number of people. And the more listener data we do in a perceptual study, the better. And we'll compile that information and find out what DDU ratios are necessary to hear a noticeable improvement in skywave interference. That will allow us then to look at the population of stations, find out how many of them actually would benefit from this. I think the answer with those Class C stations we saw in the earlier map is that they're in pretty tough shape. But what about all those Class Bs, for example, and Class As? How much do they benefit, and what stations do they need to ensure have also put in GPS disciplined oscillators so they all operate with a satisfying improvement in nighttime reception? So that's what I wanted to cover. I hope you found that interesting. And if there's time, Larry, I'd be happy to answer questions.
Sure. If anybody has any questions, you can just open up your chat box at the bottom and type a question, and we'll relate it to him. I had one question, John. If down the road your data shows that there could be some improvement to a station that goes into this synchronization, how do you go about, or is there a way that you go about to set up some sort of agreement with the other stations? Because the other stations have to do it too to make it work.
That is absolutely right. Steve and Steve Smith and Tom King would love to have all AM stations, all domestic AMs, install GPS disciplined oscillators. That's just not going to happen, especially in today's business environment and economy. So that's why I thought it would be beneficial to show any given station what their situation is through the nighttime statistical study, and it would identify which are their co-channel neighbors that they need to coordinate with. Usually it would only be 2 or 3 stations that would likely be the worst case. So it would be up to, if you were a station operator, your station and your 2 or 3 neighbors to talk and agree, hey, we all benefit from this, and it's a modest cost and easy to install, and we should go ahead and do it. Does that answer your question, Larry?
Yeah, I was wondering how you would have to get with the other stations and come to an agreement, I guess, that yes, we'll do it if you'll do it, and it'll help both of us.
Yep, right. The other thing that this study would tell us on a nationwide scale is what percent of stations are likely to benefit. Is it 30% of stations? Is it 50%? I don't know the answer until we develop those DDU ratios and run the model on a large number of stations. But we can always do this individually for your station and for another station to answer that question. What's my situation, and who do I need to coordinate with?
Has synchronization been used at all in AM in the past, or is this something new?
It's only been done experimentally. Steve did make a prototype oscillator for WSB in Atlanta, and he was hoping to do a field study by building oscillators for those other stations on 750 kilohertz, the class Bs, because WSB is the class A. But he realized that's kind of a big job to, fly around the country to install oscillators at other stations or help them. And so he hasn't done that. So right now, WSB has got a GPS disciplined oscillator, but none of those class Bs, the half a dozen or so in the US, have them. So nope, it really hasn't been tested yet.
I seem to recall you mentioned WSM and their situation there in Nashville, that if I'm correct, I remember somebody telling me that after the initial construction of that site, that was at on a Ronox tower they put up there, they actually reduced the height of the tower by some 17 feet to change their Skywave. Have you, does that have any effect on it, or does that make any difference to in this project, that you can actually change it?
That's a great point. Well, this kind of engineering analysis could be applied to a station to identify, well, who is my worst case neighbor co-channel at night, and is there something I can do with the vertical radiation pattern to either, well, really interfere with somebody else. The effort you take to change your elevation pattern doesn't benefit you, but it does benefit your co-channel neighbor. So
I didn't really understand why they did that, but they said once they went out and did the measurements, the nighttime Skywave coverage was apparently not what they wanted. And they removed 17 feet of the tower.
Well, there is an effect where the ground wave of a station at night, it extends out the same distance it does in the daytime if it's the same radiation pattern. And it's combining with the Skywave signal from that station, which of course is taking a much longer path and then bouncing off the E layer and arriving back on the ground and mixing. Those two signals can beat together. And so it sounds like what you're describing is a case where there was a population reached by the ground wave of that station, and at the same time, its skywave was arriving and causing essentially an interference with its own ground wave signal. And by changing the elevation pattern of the antenna or array in that direction, they were able to reduce their skywave, send it somewhere else effectively, and reduce interference to themselves. So
Oh yeah, that makes sense. It sure does. Here's a note from Barry who made a comment that there was a test apparently done many years ago in Chicago with a station in Lincoln, Nebraska. Some sort of synchronization test done back there. Are you aware of that, or?
No, I do know of tests that, well, not tests, but actually years of operation in Puerto Rico. An AM broadcaster there had this same kind of problem, I think we were just talking about, where its skywave interfered with its own ground wave across the island, and their solution was to operate a single frequency network. And that's not the Skywave management you're talking about, but they did that as an example. But no, I wonder if some of our participants today have heard of actual tests. It's not something that I've heard of very much. I noticed that Barry Mishkin posted a note, and Barry, maybe you could put that note up again so I could see that again, please. I think you were saying some other stations collaborated on elevation radiation pattern modification.
Well, first of all, Mark Durenberger had sent this to me, so I'm pretty sure it was CBS owned LS and KFAB, and they rigged up this huge delay system to synchronize the two stations' signals out in the field where they would otherwise cause cancellation or interference from the delay from one station to the other. The other comment I made had to do with WSM also reduced the height of their tower, and there were others, because what they found was by reducing the tower height, they moved that point of cancellation with ground wave further out from the station, and it stopped the interference in the local market.
To themselves.
Correct.
Yeah. Yeah, that antenna modification technique would certainly be helpful. And you were mentioning about the AMs actually sharing a telephone link to synchronize their carriers. That certainly would help, and that's really the principle that the AM Improvement Working Group hopes to develop, which is a low-cost GPS disciplined oscillator that stations can install. They don't need the telephone linkage anymore, and it'll cost it'll just be a one-time cost, which may be under $1,000.
John, I'm not 100% that they synchronized there between Chicago and Lincoln, the carrier, although it wouldn't surprise me. But what was amazing was for that time period, they had rigged up this delay to come up with the audio delay to match the two signals.
Oh, so it was a single frequency network then.
Yes.
Ah, well, that's, yeah, that sounds like the Puerto Rico example that I was talking about. You know, it's a little off topic, but a single frequency network for AM would be a wonderful improvement. The problem with AM, like any broadcasting, is that you have one big tower radiating a strong signal close in, which gets weaker with distance and with ground conductivity, or with FM with terrain effects. And yet their service contour goes out to a very large distance where the signal is relatively weak. And in today's RF environment, we have a lot of RF environmental noise with AM. So AM becomes principally noise limited. A single frequency network would allow a broadcaster to use multiple smaller towers that don't require a lot of real estate to distribute that signal over its service area more uniformly.
You're going to have to do some research to find this, but this was proposed in the, I believe, early 80s to do what was in that time termed cellular. And to, for instance, I think one was to ring New York with about 6 or 8 sites that, of course, the big 50s fought it tooth and nail and knocked it down. And then curiously, later on, it was the same companies that acquired the what were then crippled stations and had to deal with that. But the idea was very promising, I thought, to do what you were just saying and throw up a bunch of cells around the city, and you could, by tying the frequencies tightly, you could get that signal out there and cover the areas on the edge of what would have been coverage with a stronger signal.
Yeah, it's kind of sad that actually that technique was in popular development in the 1930s. I went back looking through Broadcasting magazine. Back in those days, it used to have a little section showing all of the engineering activity of stations. And I could look up a number of cases where it would say so-and-so station applied for a single frequency network booster transmitter. Back in the 30s, that you'd see that a few times a year being filed. And that was back when synchronizing transmitters and synchronizing their audio modulation was a lot harder than it is today. And they tried. I think in many cases they didn't really succeed. Maybe they didn't have the technical expertise and the best hardware, and it didn't work so well, and they stopped doing it. But there were many attempts to do that back in the 1930s because they realized that we could put a strong signal in one part of a city and we couldn't in another part, and we were losing potential audience. So
it looks like with the state of AM broadcasting today, a lot of these ideas can actually be put back into place, or and actually help the situation to overcome problems that we have.
Technically, it's quite possible today to synchronize carriers and modulation as a single frequency network. I've designed a number of them for FM, and they, if they're engineered well, can work beautifully to extend coverage.
I don't know that it's still in operation, but Richard Johnson referred a number of times to the pair of stations, Thinker Class 4 AMs, that were basically simulcasting in the Boston area. I think on 1400 or 1450, one or the other. But in the end, one was running dead air a good part of the time.
That's great information there. And John, I appreciate your time, and Barry, I appreciate your comments too. As always, they're very much interested. We sort of run out of time today, and don't want to overextend. I know a lot of people have other things they need to do. But John, I want to thank you for being a part of our webinar, and you're welcome to be with us anytime. Just join into us.
Thank you, Larry. I would love to do that. And thanks to all of you for hanging in there with me.
Yeah, John George, if you're still around, do you have any final comments? Or he may be on up in the mountains finding his mountain lodge that he's looking for. but we appreciate everybody joining in with us today.
Still around.
Oh, you're still there. Okay.
I'm still here. Yeah, I still am. I was listening through modern technology, and it's worked out very well as I drive along the highway. No, I don't have anything else to add. I really appreciate everyone joining us today as well. And John, this is my second time hearing the presentation, and I've learned even more this time around than I did the first time. So we really appreciate you being a part of this today.
Thank you, John. I appreciate that.
Our next webinar will be on August the 16th, and our special guest for that day will be Andy Butler, good friend of mine with PBS. And we wrote an article a few weeks ago on generator maintenance in our newsletter, and he had some very good comments. And Andy's going to be with us on that day, August 16th, to talk more about generators, proper sizing, and proper upkeep and maintenance of them. So make a note to join us on Tuesday, August the 16th for that. So we'll close the webinar for this month, and look forward to seeing you in August. Thank everybody for joining, and goodbye for now.